No, that sounds good. Great.
Okay. All right. Well, good evening, everyone, and thank you for coming for our second summer PD series event about using Javalab simulations in your chemistry classroom. I'm Kristen Vanderveen.
And I'm Sarah English.
And we are your hosts for this evening. And we've been collaborating. From the Philippines. We've got people from all over.
Nice.
Nice. And we are really just ready to get started. So, Sarah, if you want to go to the next slide.
Sounds good.
All right. I teach in Harvard, Massachusetts, which is a very small town west of Boston. And I teach honors chemistry and AP chemistry, and I'm also the department chair. I've been there. This will be my 20th year at Bromfield.
Okay, and my name is Sarah English. I teach at Sweet Home High School, which is a first ring school outside of the city of Buffalo in Buffalo, New York. I teach AP chemistry and, well, Regents chemistry, which is basically like on-level chemistry. And I'm also the advisor of our ACS chemistry club, which is the largest club at our school. And I am about to start my 25th year of teaching, which seems impossible.
And fun fact, Sarah and I were both at the University of Rochester at the same time, but we didn't know each other.
We were, which is crazy. Like Meliora, that's
Right?
So fantastic. I saw that. I'm surprised we've never brought that up, Kristen. We'll have to talk about that.
You and I have talked about it, but it just,
Yeah. Crazy.
All right. So about a year ago, Sarah and I happened to be talking chemistry as one does. And I mentioned Javalab, and she's like, oh yeah, I use Javalab. And then we came up with this idea of presenting Javalab simulations to NEACT. So here we are. I'm going to post a link to the whole slide deck here so that you can follow along. We have all the links posted in the documents. You'll definitely want to be able to go back and look at those later. And we're going to go through a bunch of different Javalab simulations, and we had a bunch of ideas for how you might use these different activities with your students. You might just show them as part of direct instruction, like here's this image and I've got it just projected on the board and I'm just going to talk about it, or embed it, a picture, or right into my notes. Is something that you could do with them. My school is really starting to explore universal design for learning, and a lot of talk about multiple representations. And I think you'll see as you go through the Javalab simulations, you'll see a lot of different ways of representing information to the students, which I think is really helpful. And I also thought that you could use them as prompts for whiteboarding or think, pair, share activities in class.
Some other ways that you could use these in your classroom is just if you wanted to embed a link into a Google Doc and have them do reflective questions. You're going to see throughout the presentation that Kristen has made a whole bunch of Desmos activities that she's wonderfully going to share with you, which is amazing. And then I use digital interactive chemistry notebooks and really focusing on three-dimensional learning using NGSS, or in New York State, we call it NISLIS, the New York State learning standards, science learning standards. So I use these Javalabs quite a bit to help support an anchoring phenomenon that occurs at the beginning of a storyline. And just one point of clarification, because I know this comes up a lot of times with people, Javalab does not use like Java. They use JavaScript, which is part of the HTML5 universe. So this is a cross-platform type of situation. It's web-based. It can be done from a desktop to a laptop to a Chromebook it's pretty across platforms, which was done purposefully by the creator. And of course, even better, it's free.
Free. I'm a big fan of free. So what we did when we were putting this presentation together is we went through a lot of Javalab simulations and organize them more or less by unit. So the units aren't listed in any particular order, just the order that I felt like putting them in. And so the first ones that we wanted to talk about were atomic structure and periodicity. And so I've got two on this screen. One was a card sorting activity, which I thought would make a great do now. Like if you're about to start talking about the history of the periodic table and introducing Mendeleev and his work, I thought this would make a great student activity. You could just share the link with the students, give it to them in your LMS, or embed it in a doc, or just send it to them by email, however you get things to the students, and have them complete it, and then it could initiate some discussion before you started talking about Mendeleev. And the other one that's on this screen is a periodic table, but what is interesting is you can click on it and it shows you protons, neutrons, and electrons. So if you are trying to talk about introductory atomic structure, just the basics of it, you can use this and zoom through it and look at different levels. And they're all interactive. They're not static pictures, so you can click on them and different things happen. And so I just thought it was cool. There are a lot of really cool things here.
All right. The next one is the Rutherford gold foil experiment, which I know my students all the time have trouble sort of visualizing exactly what is happening in terms of this experiment. Like they do some research, we talk about it a little bit, but you'll see off to the side, and I actually should have replaced this Giphy now that I made, but you'll see that on one side you have the detector, and on the other side you have a particle diagram. And what you can do basically when you open up this particular Javalab is that you can take this center point down the middle and move it back and forth. So the students can see either all the alpha particles going through this really thin piece of gold foil and how those alpha particles are behaving, or they can see the entire setup of what was happening with the gold foil experiment. So they have two perceptions of seeing it, a macroscopic and a microscopic, a real world situation, and then a model of this. So this actually, there is student interaction here, but one of the things that you could ask here is your students is, what do you see? And then what do you wonder? Which is a big part of how I start a lot of my units and a lot of my classes as well, as they're looking at different situations so that they're asking questions and they're thinking about what they're observing. So very simple, yet bring something that's relatively complex into something that's a visual for them to see.
And one of the things I really liked about that Rutherford gold foil experiment is the students can drag it from, we rarely see like an actual diagram of the setup, but they can drag it from being all macroscopic down to that particle level model, watching the alpha particles bounce off the nuclei. And I really liked that because you don't see that very often.
So true.
We have several activities about atomic structure that we found. One was, and they're similar to each other, they're related. So there's one about flame tests where students can actually simulate flame tests, and it really relates it to the Bohr model. And Sarah made a Giphy to sort of show you in real what it looks like when the students are interacting with them. And they also have one about fireworks. And Sarah, I think you've also integrated this into an interactive notebook, have you not?
That I have. So the fireworks one is great because that is my anchoring phenomenon for and I think this performance expectation is the same whether you're using NGSS or an NIST list for New York State. So one of the things that I really love about Javalabs is that there's no embedded questions. There's no forced way of how you need to use a simulation. So you can see the Giphy that I made off to the right. And then you can also see how my students would see it as part of their interactive notebook. So if you look over on the left, there's directions for them to, click on the image, and I'd probably have this projected too, but just in case a kid was absent. So they would click on this image right here, and then the link would come up that would take them to that particular Javalab. And then what I'm having them do is clicking on each compound, recording a firework color, and then we're looking for patterns. We're trying to figure out like what is distinguishing that particular firework color. Is it the cation? Is it the anion? What trends do we see? The only problem that I had with this particular simulation, even though I absolutely adore it, and I did write, I sent a message to the developer about this, was that the barium nitrate one looks definitely very similar to the copper compounds. And I was like, hey, maybe you could make this a little bit more green and not looking gray. But that's just a way that I'm using it. The nice thing is that there's all sorts of different ways that you can use it, and you're not forced to use it in one particular aspect.
And which is one of the things I really like about it. Okay. About Javalab in general, it's very flexible. They've got a nice activity for electromagnetic waves. And this is a static picture, but if you go into the actual Javalab activity, you can drag it along to go to different regions of the wavelength of the spectrum, and it'll talk about the wavelength. So you could use it as, oh, this must be a Sarah slide. No, I'm ahead of myself.
Oh no, you're
No, I'm
fine.
good.
This is you.
I thought it was a great prompt for a whole class discussion, especially if you're teaching a class where you're not so worried about, wavelength energy frequency calculations, but you really want them to have that, relationship between wavelengths and energy. You can really be exploring that here, just visually. It can be a nice part. You can use it as part of your whole class discussion, or have the kids explore it and turn and talk, and just what do you see as you go through your lesson for that day.
Awesome. All right. Then the next one that we had was this spectrum of the hydrogen atom. And
I love this one.
Yeah, this one's great because you could see off to the right with that Giphy. So you have the ability to click on the electron. There's one, actually, you might be able to move. I can't remember if you can move. Oh, no, you can. Oh, look, it's showing me right there in the Giphy. You can move either of those electrons. So you can move an electron like away going so that it's absorbing energy or it's releasing energy. If you have it set up where it's absorbing energy, you're not going to see any energy left off, and you have those positive values associated with it. But then when it's releasing energy, you can see those little lines representing the different wavelengths of energy showing off. And then again, it's also going to correspond to what part of the electromagnetic spectrum that's associated with. So which is fantastic. So they're showing the difference between absorption, like going from excited state to ground state, or ground state to excited state.
Yeah, I really, really like that. I think it makes it really obvious to the students what's going on. There really are a lot of good atomic structure simulations at Javalab. And if we go to the next slide, there's one on Bohr models. And again, this is clickable, so you can click on whichever one you want or a whole column. And so it can be a great way to talk about some periodic trends, relating that to Bohr models. And it's also a good way to talk about benefits and limitations of the models.
Right, because if you click on the models, you can definitely, like, let's say atomic radius, right? So you can definitely see that the atomic radius as you're moving down a group is going to get larger. But as in many situations, they don't show that atomic radius is getting smaller as you're moving across a period. So that's a great moment, a teachable moment, saying this is just a simulation. It's very, very simplistic. There's a lot that we can do with this, but like any type of simulation, it is going to have its limitations. Now, would it have been awesome if the developer could have done that? Yeah, but that's okay. It's a teachable moment. Okay, then we have this electron configuration one that looks at it from a different perspective. So now we're dealing with S, P, D, and F. And in the world of New York State, we don't teach that to our students. We still live in the world of the Bohr model. But with my AP students, this is a great visual to show them how the electron shells are filling, the different sublevels and principal energy levels are filling over time. And one thing that I think is good is, because I teach this, is showing overlap. So it is showing how you know, that the 3D sublevel is going to fill before the 4S2 or before the 4S sublevel. So that's a really nice thing for them to see as they move this through this. And also showing the overall nuclear charge, which I also think is a good thing to draw their attention to.
Yeah, there are just so many great simulations. There are a bunch of simulations to explore chemical formulas. And so this one for molecular models, it's really meant as a whiteboard kind of activity. So I anticipate using it to just illustrate compounds for class or molecules. And, you just drag the atoms that you want onto the board. So if you just want to, if maybe you just want some pictures that you can, and screenshot and put into other presentations, or you want to just draw things up on the board so students can see them. I think it's just a really nice way. And I also thought this was one of the two simulations that you could potentially use to talk about empirical, just to help visualize empirical and molecular formulas. Like they've got, an alkane on there. You could have series of those and showing how, the empirical versus molecular formulas, I thought was useful.
Think too that this particular one, I think there's a line feature to this one.
I think
where,
so, yeah.
Where you can actually draw lines like to represent bonding in between the different symbols. Can't remember though. I'm pretty sure it is that one. This one.
Oh, this is the best one.
It really is, because I remember during COVID, I actually cut all of these out and made things, and then I made we won't even go into the detail that I went to make this particular this particular activity.
I mean,
Like
activities that have you, doing matching cards up in different ways. It's been around for a long time. That's not new. It's just that it's here and you don't have to cut things out.
Right. And you could definitely use this as part of a lab where the kids would build something and then take a screenshot of it, and then you can ask about, what did I say? You can focus on what does it take to create a neutral compound, and the role between positive and negative ions, and then the ratio between those positive and negative ions, and how that translates over to writing a chemical formula. And I think because I was limited to like a 30-second limit, but it really shows, especially when you're building that AL3 or was it AL203?
Yeah.
Just how much the kids really have to work on getting those things together to really make that electrically neutral, and how you would take those individual pieces and translate that into a formula.
Mm-hmm. And what I did is, if I don't know if you guys use quizzes or not, that's okay. I wrote a multiple choice quizzes activity that links to this simulation, and it's really just multiple choice questions. If these are the two ions, what formula it would be? But it's using the ions here first with binary compounds, and then using them with polyatomic ions. Another way to help students practice that. Eventually, of course, we'd love them to get to the point where they don't need these kinds of manipulatives, but it's certainly a good way to get them started, or, if that's what is the right level for your class. So I made that available to everyone. If you go to quizzes, or you can set up a free account at quizzes and use that with your students.
Absolutely. Which leads us to the molar mass calculator.
Oh, I like this one a lot too.
So this one's really interesting because you can actually have students calculate the molar mass by putting in the formula. So the way that I visualize this working is definitely not telling the kids about this prior to teaching how to calculate gram formula mass, molar mass, and then having them do a bunch of worked problems. And instead of saying, hey, look, here's a PDF of an answer key, why don't you check your work? But actually having them come here and use this to figure out what the molar mass of each of the compounds that they calculated would be. And the other thing is, Kristen, that I think about is they don't have parentheses here. So that would be an interesting thing to see, to how they would have to, if they would understand that to use this molar mass calculator, that you would have to distribute that, the numbers.
Right, right.
Just thought of that. So that would be an
Right.
interesting perspective for
Yeah,
them.
that because when I wrote the simulation, I wrote an answer, a problem set to go along with that, and I have the right. So I'd have to update that to match that, or just thinking about, well, how's my work to do the problem versus what does the Javalab simulation give me, and thinking about that I think I need to add part to my questions. I'll go back and add that in, like, how do we, what do the parentheses mean, and distributing that.
Right. And I think that's brings up a really good point about using the Java Labs, is that you always want to make sure that that you practice these ahead of time, that you really work with them and figuring out like what's your purpose for using these. Because like any simulation, it's going to have its limitations. But at the same time, it's super powerful at the same moment. So just good things to keep in mind as you're working through these.
There were two other activities that involved just representing organic molecules, and again, these are sort of whiteboard activities. So there was one on alkanes, so you could just drag colored circles over the way you want them. And there's a note in the activity how it's not necessarily going to give correct geometries, but if you just wanted to show, say, alkane chains, to introduce that idea, or just ways of representing molecules, that could be really helpful. And again, I thought you could use this in terms of empirical and molecular formulas, even if it's just to create visuals for your own presentations. And one on hydrocarbons, again, where you can drag them over. And Sarah had pointed this out when we were looking at this last week, how the hydrocarbons one really emphasizes the octet rule as you're looking at molecules and really trying to make sure all of your atoms are following that octet rule, because it's showing those valence electrons, which is just something else to keep in mind as you're working through.
And thinking about what you just said, Kristen, I didn't even think about the idea that you can build molecules in this, even if you don't have your students working with them, and then you take it to something like what is it that you take a screenshot of the molecule that you just built, and then you get like background eraser, and then you can remove the background, and then you have like ready to go molecules rather than trying to build them in some other program. Like I know I build a lot of my structures in Keynote and take screenshots and then use background eraser to just make sure that it's a transparent molecule, but you could just make them in here, which would be, who are we kidding, a lot easier. So
anything
yeah,
you can do to make those representations easier for yourself, and now you've got screenshots and you're ready to go.
it's true. All right, so molecular polarity, always an interesting topic with the kids. So two different Javalab here. The first one on the left is polar versus nonpolar. So if I think there's a button on the bottom that says like run. And when you hit run, the circuits on each of these will close. And then obviously our polar molecules here will align themselves and line up in fields. So they can see that the little molecules are going to, the polar molecules are going to orient themselves between the positive and negative poles. While when you complete the system with the one over on the right, it does nothing. Those little diatomic nonpolar molecules just keep on just moving around like nothing happened. So interesting concept there for students to reflect on. And then even though I think I'm going to move away from this particular phenomenon after talking to my brother today about phenomenon, because he's my only sibling and we're both chemistry teachers, we do use the balloon, like that you take the balloon and you rub it on your head, and it's it has a charge associated with it, and then you bring it next to the burette with water, and then we bring it next to a burette with like grapeseed oil in it, because you can't use vegetable oil because that's too heavy through a burette, we've discovered, but grapeseed oil works out just perfectly. But this particular model does a nice job at showing how these molecules would orient themselves, and we're assuming it's water, well, representations of well, actually just a polar versus a nonpolar molecule, and how they would orient themselves towards that magnet that person is holding versus the molecule over on the right, which is a nonpolar molecule, and how that magnet is not affecting it. So, I mean, there's two ways that you can actually use this particular simulation. You can definitely use it for molecular polarity, but then you can also use it just with possibly, depending on how the molecules are moving through, with intermolecular forces, depending on how those molecules are aligning themselves as they come out of that, what we're assuming is a burette as they're coming through. So lots of stuff to play with here too. And I think Kristen made a Desmos about this as well.
I have a Desmos activity that I wrote for, I think it's for my AP classes, where I incorporate the polar versus nonpolar molecules as one of the screens in there. So there's a lot more in that Desmos activity, but it's just another piece of the puzzle as the students explore, which I find to always be very helpful.
All right. Next, we're on to chemical bonding.
Yeah, so they had two simple simulations to show covalent bonds and ionic bonds. Again, these are, I just did screenshots of, a couple, but you can use this to introduce these topics or review the topics, really emphasizing the octet rule again with both of these. So that's something that is just worth noting. It does show the nuclear charge as well. So you can, one way of representing a covalent bond, the ionic bonds, where you end up showing the transfer of electrons, and you've got oppositely charged ions that are attracted to each other. And so that electron transfer piece, just another way to, help refresh students' memory, or another way to just explore that.
All right. And then they had a super fun one on metallic bonding.
Oh, I really like this one too.
So they have this hammer that's hammering on this piece of metal. So it's showing that positive nuclear charge. They're showing that mobile sea of electrons, like my kids are like, that's all I got to remember is sea of electrons for metallic bonding. But how we have delocalized electrons and how they're moving. We're also showing that we're looking at this, and the idea of malleability, that the metals are able to be bent. And that really is the extent. Like, you've seen the entire Javalab right there. The kid is pounding the metal plate with the hammer, but that's the extent of it.
And yet, do you need more? I mean, like it does what you need. So I really like that. I wrote a little activity to go along with this, with a little vocabulary and then just some questions. It goes a little farther than just this as well. But I thought it was, if you could easily be a homework assignment just to review metallic bonding.
Right. All right. Our next topic is gases.
Oh, yeah, there's a lot with gases. They really went to town. There are 3 different versions of Boyle's Law Javalabs. One where you're really compressing the volume, one where you are changing the weight, different ways of getting the graphs, and one with the J-tube for Boyle's Law, which is how he did his original experiments. So a couple of different perspectives for how you can get that data, and representing it graphically as well, which is something that we want the students to be able to do. So we thought those different perspectives were useful, and depending on what you wanted to emphasize with your students, you could pick Boyle's Law version 1 or Boyle's Law version 2, or if you want to go a little deeper into history, looking at the J-tube version, which doesn't really provide a graph, but just as another representation, big on different kinds of representations.
One of the things I really like about these 3, or at least the 2 with the graphs, is that you have both a particle diagram going on and the graph that's representing what they're seeing. And the fact that, and I don't think this was very common in a lot of the simulations that he developed, but there is a way in this one where you can download the data. You can get a CSV file based on what you want students to do with it. So with a lot of these simulations, to me, it's more of a reflective process, and I think, I wonder type of situation. But with definitely the Boyle's Law and the Boyle's Law 1 and the Boyle's Law 2, you could actually make an entire lab out of that if you just wanted the students to really look at the relationship that's going on in these simulations. So that is something that is not typically seen in a lot of the simulations, the ability to download the data if you wanted to. The next one is this Charles Law simulation, which I love and adore. So basically what you're doing here, and so you could see the simulation off on the left and then the graphical version of this on the right. So two different simulations for this one. I used the Charles Law one on the left in one of my digital interactive notebooks where we followed the adventures of Party Balloon. Party Balloon did a lot of traveling. And so one of the things that I was trying to do was look at this balloon in terms of different temperatures. So they were making observations of what happens when the balloon goes outside in cold air versus comes into a warm house. And then we were relating it back to the observations they made as they moved that black dot up and down that axis right there, up and down that line. So they can draw conclusions about if I raise the temperature, what's happening to the behavior of the particles, what's happening to the volume. So that's one of the things that I did with that.
All right, and just to round out the gas laws, I love your idea of party balloon, Sarah. Now I want to call it Party Balloon all the time.
The Adventures of Party Balloon. I'll have to show you.
Did Party Balloon explore Avogadro's law? Because there's a Javalab for that. It's not a very difficult law really to understand, but sometimes I struggle with how to introduce it to the students. So I liked that this was something I could use as a class discussion to develop the idea, right? That if we have the same number of particles at the same pressure and temperature, they're going to have the same volume, and that allows us to explore that and see that idea a little bit, because you can play around with what molecules are in your sample, and they can have different formulas, and some of them are diatomic and some of them are monatomic gases, etc. And I just thought that was a nice introduction. I think I would probably embed that into my gases presentations. And then the other thing that I found was the combined gas law one, where you explore pressure, volume, temperature for gases. It's hard for students to think about if you're changing multiple variables in the combined gas law, really trying to think about that on a particle level, and you can play with that. I almost think this one needs like a problem set to go with it. Like just exploring it would be kind of a little too vague, but sort of like, well, what do you notice if you do this and this, and how do the particles change? Because you've got the particle level model and data as you play around with the different features. So I really liked that too.
Yeah, a really nice representation of both the particle diagram and the math to back it up, which I totally agree with you on that. So we're moving away from our amazing amount of gases Java labs over to our Java simulations, over to nuclear chemistry. Now I think there's only one that deals with this, but again, very, very simple. So in the beginning, you have all of the gold coins showing, and then you basically hit, you set, it's like run simulation, and it will go, the graph will go part way, and half of the gold coins will flipped, and then you hit the simulation again, half of them will go away, and it will be reflected on the graph. So the students can basically count the remaining coins, look at the half-life that goes by. So it's just a very simple way of just showing half-life represented instead of like dragging out an entire lab. So it's just something really simple and quick to show half-life.
But I also like when you run the simulation, the coins don't all sort of flip at the same time. Like that randomness that it's easy for students to like, oh, half-life, everyone's going to shift now. No, that's not, the decay doesn't happen altogether. And that was something that I thought the simulation helped reinforce, that it's sort of they're changing randomly. And then, we're just looking at how much time it took for half of them to switch. There is another radioactive decay. There's one for chain reactions.
Oh, yeah, that's right.
For
Forgot
nuclear
about
chain reactions. So I didn't include that, but there are other simulations. We didn't include all of them. There are a lot, actually.
Yeah, it's actually amazing how many simulations there are. And then it's just to think that these are just the simulations for chemistry. Javalab also has simulations for biology, earth science, space, and then math, technology, measurement. It's really astounding how
Electricity
many
and
simulations.
magnetism and mechanics.
Yes. Oh yeah,
There's so
physics.
many.
It there really is.
I mean,
So
this
now
is
we're
like
gonna
life's
go ahead.
work kind of thing. All right. So there are a number of simulations for chemical reactions, several to help you explore classes of reactions. I really liked the precipitation reactions one, where you can choose what substances start in the reaction and then they start moving around. And if it's a reaction that would actually form a precipitate, you see it settling out in proportion based on how many um, ions of each type you started with. And so you can see which ones remain in solution and you can see the ones settling to the bottom. And I really liked that. I liked it so much that I wrote a Desmos activity for my AP classes that I use early in the year with my students. And we explore this to help review writing the reactions, but also reinforcing the idea of those spectator ions, because it was a nice visual way to get the students working on that skill, because that's hard.
And just to note, I had to speed up the clip speed on this, so this is running at a really fast clip speed when I made this little Giphy, just because it does take a little while for these to sort of float around and hit each other. So when you do play with this one, don't be like, why is it moving so slow in my simulation? No, your computer's just fine. It's just I wanted to show a bunch of different ones as we were showing this particular thing. And I agree with Kristen. I mean, I love this idea, especially with AP showing the idea of like limiting reagents and leftover ions. Not everything's going to be consumed. It's just fantastic. This is definitely one of my favorites.
But I really like this one too on acid-base reactions. So there's a whole sim for neutralization reactions. You can pick which acid you want. You can pick which base you want. You can figure out how many you want of each kind, and it will show the products forming. Of course, water just sort of fades into the background, which I really like how that was done. And so I can see using this with your students to really think about the pattern of if it's not just a double displacement reaction, but I form water, we form this ionic compound. Sometimes it's a precipitate, sometimes ions stay in solution. Thinking about the stoichiometry of it, that's how I anticipate using it myself, but I can imagine lots of ways to use these different simulations. And I think the more creative you get, the more fun you'll have.
Absolutely. Like these are just a springboard. So, I
Right.
mean, to me, this is just the beginning part of having kids have a visual, and then you push them in a different direction where they're doing something maybe a little bit more complicated. But just like
Or
Kristen said, I mean, one of my favorite things about this is that not only is it showing a neutralization reaction, but it's also showing something precipitate out as well, which is why I picked this particular combination for that one.
because it'd be
And
easy to say, okay, well, here are the reactants. Now work on writing balanced equations. Your AP students, you might be, okay, now you're going to write ionic equations and looking for patterns. If it's a strong acid with a strong base and thinking about some of those. So there's just a lot to do with that, which I really like. All right.
right.
I think we had one more about single replacement reactions.
Single replacement reactions. So this one is on the activity series. So, and I forgot to click on this one to look at
Oh,
it,
it's okay.
which is terrible. But I think the general idea here is that you have some type of electrode that's being placed in, or just sorry, not an electrode. I'm automatically into the world. I look at that and I'm thinking, oh, it's a half cell, but we're not there. So a piece of metal in a beaker with a solution. And we're seeing how, we have, what is this? It's now we're showing like a zoom in bubble, right? So we have copper metal, and we have silver, and just the whole single replacement. I'm wondering, Kristen, if I can actually click on it and take it, if
Yeah,
we have time.
sure. I think we're in good shape. Mhm.
So if I click on this and it takes us over. So again, like we were talking about before, work and energy. Forgot to mention that one.
Right. And there are a lot of simulations here.
Yeah, and then the etc. part,
I
so
haven't even explored that.
I know. So he's got VR stuff, he's got just wow. So okay, so look, we can change the metal plate. Let's see. What are we feeling? So we could do a nice zinc metal, and the solution, we could just do copper right there. So there we go. So
You have
if
to
we
hit run. Yeah.
run, um, so we're basically seeing the activity series in play, coming in right here. So we can talk about this in terms of the activity series, but at the same time, we could also talk about this in terms of oxidation and reduction reactions, without a
Mhm.
doubt.
Right.
So this is Javalab's
And reactions that don't happen too, right? Because you can have all the choices. So,
right. We
if
switch
you
this around to
switch it around to
copper.
something copper and, you know,
We'll just do the opposite, right?
right,
Well,
where
oops.
no reaction occurs. And it's just because I can write a balanced equation doesn't mean the reaction actually takes place as written, and just exploring some of those ideas that just because the particles collide doesn't mean anything's going to happen, right? And then you could extend it into what's getting oxidized, what's getting reduced, if that's what you're doing with your classes. So some really good simulations there.
Right. So you could actually have them check their reactions.
Mm-hmm.
Let's see. Now, let's see, let's get back to our slideshow here. There we go.
And I did write a quizzes activity for, it's really probably for a first year class, just about exploring single replacement reactions and again, using the simulation to explore them.
So I love that one. Now that I know, there's just so much that you could use pretty much with every single unit or storyline that you're doing that could support your students in a visual type of way.
Mm-hmm, mm-hmm.
So, on to chemical equilibrium.
Now there's not a lot with equilibrium, but the ones they have are really good. I really like this equilibrium constant one because you can manipulate how many reactant particles and how many product particles, a very simple generic reaction, but manipulating that, and it actually shows the reds turning to blues and the blues turning to red based on what you've set it up to be, and it will calculate the equilibrium constant for you, so you can explore that idea of, if I've got more reactants than products, KAQ is small. If I've got more products than reactants, KAQ is going to be greater than 1. And I did incorporate that into my Desmos activity so that you can explore that. And which is, it's just, again, a visual way, because I know that in AP Chem, knowing that, being able to make that connection is helpful. And then there's a Le Chatelier's principle one, and this is volumes of gases, and how volume of the gas sample will affect the equilibrium position. So you can actually explore that visually a little bit. That is one of the harder Le Chatelier's shifts sometimes to get across to students. And so you can literally move the piston and it will change the volume, and you'll see, the number of reactant molecules versus the number of product molecules change as a result of your shift, which is a great visual again for that.
Absolutely. Le Chatelier is never easy to teach.
No, but that one is the hardest of them.
It's true. Now we get into the ones that I've definitely used a lot this year, and this is the ones that deal with specific heat capacity or specific heat changes in water. So I've definitely used these a lot with my students, and they really, really have enjoyed using these ones. So the first one is just visualizing melting point and heat of fusion. So they're seeing basically a phase change curve. They're noticing what's happening both in a particle diagram type of way and reflected over in a graphical type of way of what's happening to this water as constant temperature, a constant amount of heat is being added. So you can see over on the left how I've tried to draw their attention to talking about, all right, what's the physical phase of the substance in the beaker? The initial, and that was done before the simulation was even started. We were talking about how would you represent a particle diagram of a solid or recognize that, and then looking at the initial temperature, and then it's got the prompting questions that go along with it to make them think about what they're observing as this simulation is occurring. And again, with this one, all you're doing is hitting run and making observations, but there's a lot to process in this one if you really dig down deep into it. The next one that I did was this visualizing specific heat capacity. And with this one, we have it aligned with that particular performance expectation. And you're thinking about noticing how energy travels through something that has small heat capacities like a metal versus a large heat capacity like water, and just watching. And the kids are mesmerized as they watch this occur, because they can see the changes in colors from like a purple color to a red and how it spreads throughout the particular substance that you're looking at, and then trying to get them to talk about in their own words of what they think is happening. So really love that one.
And I love how it shows the particles vibrating in the, with the conduction and movement with that, not just color coding it, but the particles are moving and colliding with each other. You see that a lot in the next one, actually. I'm getting ahead of myself.
No, but it's true. I mean, I totally forgot to mention that, because that's very, very, very true about how it's not just actually the colors, but the particles moving themselves. And this one is great. And the kids are totally mesmerized about this one. So you have this blue square over on the right, and then this multicolored square over on the left. And all you're doing is just moving the square, the one on the right, to basically touch. So we're talking about thermal conduction here, transfer of energy, and how it's moving throughout, and how the particles are really not moving very much to suddenly moving in the same type of way as the substance over on the left. So, we have a key associated with this. And again, all I'm having my students do is really just tell me what you think is happening. So they're trying to get their thoughts down on paper, instead of just passively sitting there and just looking at the simulation. And then we'll call on it and see if we have different perspectives about what the kids notice. Some might notice the movement of the colors. Some of them might notice how fast they're moving. So it just definitely opens up a conversation with that one. All right. So final thoughts in our last 11 minutes. I'm sorry. So my particular final thoughts, when you're using these, definitely be purposeful. I'm definitely in the space now, as I've finished up my 24th year of teaching, that I'm really trying to make sure that whatever I'm doing in class, there's a purpose behind it. So I'm not going to show a simulation just for giggles and I'm thinking it's cool. I want to make sure that it is very specific of how I want to tie that back to support a particular phenomenon, because we are definitely in New York State moving heavily towards assessing three-dimensional learning. And I can see how Javalabs are going to play a significant role, especially in terms of the modeling component of it, as a science and engineering practice, versus analyzing and interpreting data, asking questions. There's a lot of very good ways of using science and engineering practices and cross-cutting concepts with these particular simulations to get kids' thoughts down and captured so they can be part of a conversation. So my second bullet pretty much is already saying that. How is the simulation important to supporting your anchoring phenomenon or even an analogous phenomenon? And then my biggest thing and my takeaway, especially after with the fireworks one, where all I had to do to really fix it was to just give some colors ahead of time, but making sure that you're previewing the simulations before you use them in class and that they're going to work for you and your students.
As I was working through this, some of the simulations that I have used with my students, I do find if it's too open-ended, the students won't know what to do. I suggest giving them specific suggestions. Okay, what do you observe? Turn and talk, or have some questions that go along with it so that they have something specific to do, rather than just, oh, well, look at this, that's cool. And I think that's just good strategy for classes anyway. And we've mentioned this several times throughout the presentation tonight, those connections between the particle level models and macroscopic behaviors. That's one of the difficult things we're trying to do with our students in our chemistry classes, is helping them to think about the phenomena on different levels. And these simulations can really help with that. And my other advice is to just try it. If you think it's going to work, check it out. If you have a problem set that you think goes along with it, go for it. If you want to try whiteboarding, try. If it doesn't work well, you'll do something next time that works better. It doesn't have to be perfect the first time, but I think you're really going to like using these with your students.
Totally agree. So we just wanted to wrap up. Oops, let me go back one. Just a little bit of information about staying in touch. There's all our information right there. I'd also like to give a shout out to my good friend, Ashley Green, who was the person that originally introduced me to these a couple of years ago. So wouldn't be presenting on this without Ashley making sure that I knew that these actually existed. So
there are a couple of questions that came up in the chat that really address you. One person, I think it was Donna, asked, what do you use to create your digital interactive notebooks?
Oh, sure. Well, why don't I stop sharing? There's my cute little.
And then we're going to put a plug in for NEACT too before we go.
Oh, absolutely. So to use to create my digital interactive notebooks, I'm just using Google Slides. Nothing fancy. I have seen people use OneNote for digital interactive notebooks. Some of my friends just use Notability, and they have stuff through them that they've used. But I try to keep, I don't want to, other than my school being G Suite for Education school, I didn't want to have to buy any type of special program, because anytime that I have to buy something, they tend to go away, and then all of my good work goes away, and then I'm sad, and I hate that with a burning passion, which is why I like Javalabs, because it's free. So even if this particular developer doesn't make any more Javalabs, they're just still going to be out there until the internet dies. So there's that. But yeah, if you ever want a copy of one of the notebooks, if you're thinking about doing something like that, you're more than welcome to them. I give them away and I say, have at it.
Yes, because that was one of the other requests from Dawn about.
Thank you. I am thinking about doing that this year. I'm interested in creating an interactive notebook. So thank you for that.
Yeah, just email me. When I was at ChemEd, I did a whole presentation and used the notebooks as a backdrop and just said, hey, here you go. I could show you how to change it up however you'd like. Don't need any credit. Don't worry. Somebody else in this world has already used all the content. So it does not belong to me. It belongs to everybody. So it's fine. So just email me and just let me know what you want.
Okay.
Yeah, not a problem.
And so for just to wrap things up, if we can answer more questions, I'm certainly not in a rush to go. But this session was hosted by the New England Association of Chemistry Teachers as part of our summer PD series. I'm the immediate past president. I was president for 4 years, and my term basically ended on Tuesday. And so we do encourage you to join NEACT, and I just posted the link in the chat. Your membership helps us to continue to be able to provide these events. We have some events that are members only. A number of our online events are free, but we need our members to keep this going. And if you're not a member, we strongly encourage you to do that. There was a question about Desmos in class. I have a whole series of Desmos activities written for different levels. I can share a Padlet with them for you, and that's like a whole session all by itself. I could talk about that, and have talked about that at AP Teach and NEACT quite extensively, actually.
Yeah, and somebody wrote, is there an empty interactive notebook that you could show us? You know, it's so the notebooks that I have, a lot of them are like based off of 3-dimensional learning. So Don, if you just want to shoot me an email sometime, we could set up a Zoom meeting and I can show you it. Be more than happy to do that sometime. Because that is not a conversation to be to bridge lightly. So I don't want to overwhelm our the focus of our presentation for tonight, but yeah, I'd be happy to, you know what, Kristen, anytime you'd want me to come back to talk about digital interactive notebooks, I'd be happy.
We're always happy to have you talk, Sarah.
I like talking to my people, so it's great. It's all good.
Nothing better than talking about chemistry with like-minded chemistry teachers.
This is true. It's very true. But I definitely encourage you, though, if you teach something other than chemistry, to check out some of the other simulations. I mean, I clicked over, I don't know if it was the technology one or the physics one, but he had all this stuff going on where he was showing you equipment about and how to like hook things up and then how to gather data. It was really pretty wild. I was like, I have no idea what's going on right now, but it looked really, really neat.
There was a question about Desmos activities too. Again, that's not really the focus of tonight, and I can talk about Desmos for hours and using that, but I actually I made a video on how to
I'm a teacher just like you. I teach 6th grade science.
Sorry, trying to get the link for that. For creating activities in classes, I would say play with the activities that I posted in the Padlet. And if you want to talk Desmos, I'm more than happy to do that, but maybe not tonight.
So did somebody else have a question for those of you who are still sticking around? I thought I heard somebody and then got lost in the conversation. Or not.
Or not. I'm going to stop the recording because I think we're